It's kind of nice if you want to practice or improve your coding ability, figure out what the heck they're doing. But one thing we'll always do with any of these state-space controllers is minimum realization. You check on that first thing. So let's see what they're doing. So, as we've seen, there's an infinite number of realizations of a system. We've got a controllable form, observable form, physical variables, whatever. And they'll have advantages, disadvantages. And the number of states can vary, right? And that's where the problem comes in. We get these controllability and observability problems because of this. So what we want to do when we're designing controllers is find that minimal size. And there's a thing called coprimeness. It's a word definition you got to know. If two polynomials have no common factors, then they're called coprime. That's basic mathematical definition. For example here, you have a polynomial numerator, polynomial denominator. Usually it means we have no pole zero cancellations because there's no common root or a factor of the numerator and denominator. All right, so what we're going to do is check for coprimeness, and if it's not coprime, what do we do? Well, went through this thing about, hey, I have some transfer function, how do I write these state equations for that? And we can kind of do it essentially by substitution, right? Kind of went through the whole routine of that. We showed that, hey, all I have to do is write these coefficients in the right form, and I can put them into what we call controllable form, controllable canonical form. What are the forms here? Where in this form, all of the coefficients of the characteristic equation are in a row. All of the zero coefficients are in the output matrix. That's one of the forms we can do. Essentially what we're doing is using what, if you remember, almost the very first couple of weeks of classes, we use a pseudo state to get rid of these derivatives in the input. I don't want derivatives on any of my inputs. Okay? So we did that, if you remember, times 0, a transfer function of whatever. And this is output of input. What we did is say, hey, let's split this thing up into two parts. I can say this is like a z over u times a u over y times. Z over u, z, y. Thank you. Where this one is simply this one plus that part. So you split it in two parts. That's z is this pseudo state. Right? Remember how we did that. All right. So if you look at the controllability matrix for this thing, it's in control. Notice it's in controllable form. You'll see something interesting shows up. Is that we'll get these ones in the diagonal. All right? Parallels occur. All these other coefficients show up in this either upper or lower triangle depending on what form they have. So if I have all ones in the diagonal, what can I say about the rank of this matrix?
It's 4.
It's 4. It doesn't matter what any of these things are. Right? Because essentially I have ones and diagonals. It's going to guarantee it's going to be full rank, because any other things I multiply times 0. And I have to do the determinant on that. Right? So, right note, that's why it's called controllable form. Okay? So if I have it in this A matrix in that form, the controllability matrix will end up in this form. Okay? That's where the name comes from. So it's actually quite convenient. Okay, so let's look at coprime kindness for observability. And give you the note of the theorems and stuff both of this stuff. So if the system is not co-prime and the system is not completely observable, this means my state are not getting to the outputs. One thing to note is that if we do have this pole zero cancellation, the root's still there. I just can't see it because of the cancellation. Right? That root of the system still exists, but I'm not able to see what's going on. Hopefully that root is stable and we're okay. So it's like the same thing in observable form. So this is so-called canonical observable form, where we have all the coefficients of the characteristic gradient now in a column, not a row. Right? All of the zero terms end up in the B matrix. Right? And if I look at the observability matrix, the same kind of pattern shows up. A whole row of, or diagonal of ones. Right? So this is, if I have all these ones in the diagonal, this is guaranteed observable. Why it's called observable form, right? Because the observability matrix has this nice pattern to it, right? All right. So it's completely observable because they have ones in the diagonal, what's called that. Essentially, these are dual. You know what dual is in mathematics? Is if dual here is if this is shown in controllable, the duality is observability. Basically, it's the same math. It's just slightly inverted in each other. All right. So think about the pole zero cancellation. You might be able to see the root, but it can't do anything about it. It means it's not controllable. Root's still there, right? So not controllable. I can see it, can't control it. Not observable. I might be able to control it, but I can't see it. Or it might be a case I can't see it or control it. So let's look at this. We can transform between the controllable forms and observable forms by this simple matrix, which is kind of like the vanity matrix, but the diagonal is going the other direction. This will transform anything from controllable form to observable form, or observable to controllable form. Right? Example. Here's something that's did this in MATLAB. Here's it in controllable form, right? Row of coefficients in the first row. B is 1, C has all the coefficients as 0. Controllability, rank 3. Observability, rank 2. All right? So it's controllable, but not observable. We look at the transfer function of this thing, so I converted it to the transfer function. And you'll see that, boom, I've got a pole zero cancellation here. Not obvious in the state form, but it is obvious in the transfer function. So it's a common factor, it's not co-prime. Now, if you look at this thing, how MATLAB realizes this transfer function, so I put it back and had MATLAB solve for the A, B, C, and D matrix. So valid, just notice it's not quite in the controllable form. What's the equivalence transformation on this? So again, here's the system controllable form. And my P matrix, which I forgot. I did that. Which is the diagonal or off diagonal of all ones. Multiply my A matrix times that, and I have it in observable form. Okay. In fact, all I have to do is find the transpose of it, and I'll put it in observable form. Okay. So being able to do transposes between observable and controllable, easy way of doing it. If you look at controllability and observability, in this case, it's not controllable, but observable, when I put it into observable form. All right? When I had it in controllable form, it was controllable, but not observable. When I transform it to observable form, it's now observable, but not controllable. Same full zero cancellation formula. Okay. Now, there's a way of removing this common factor, and it's called min-rel does this. Right? So, MATLAB has this thing called min-rel. Look up the help file on that. And what it'll give me, it removes that common factor from it and gives me the minimal realization, which now is a 2 by 2. Right? Because I can only control and observe 2 of the states. Okay? And that'll give me those 2 states. Right? So in controllable form, gives me the states. Transform it to the, using having MATLAB transform it, gives it in the not necessarily base form. Right? All right. So, is it a minimum realization? So this is the theorem out of the book. This kind of states it. So a state space equation with A, B, C, D matrix is minimal realization if a proper rational function G, if and only if A and B is controllable, A and C observable, or if and only if the dimension of A is the same as the degree of this function G. Right? So basically, it's stating that it's a minimum realization if it's both controllable and observable. And other theorem in this one is that all minimum realizations are equivalent. Doesn't matter what form it is, it's essentially equivalent form. Right? So, process of designing controllers. Get your model. Check what? Controllability and observability. Okay? If it's not controllable and observable, you need to find the minimum realization. Right? It says, I can't deal with one of these states, so here's the minimum set of states I can control and observe. Then we can go through and design the controller. So that's the process. Makes sense? Yeah. Interesting examples. Okay. Let's get into design. So we're going to start doing some controller design. We're really trying to get to here. 2 general methods. We'll look at both of them in this class. We'll concentrate on the first one. We can define where the characteristic roots will be. I can define all of them. Right? Not just dominant roots like we did in transfer function control, but I'll specify every single root. That's one method. The other method is basically by defining quantities on the states. Example of that. One of the states might be a position. So I want to minimize deviation from that desired position. Right? A state might involve energy. So I might want to minimize how much energy is spent. Right? Might be a penalty not really meeting the states, like time. I want to design a controller that minimizes time. It helps get from point A to point B as fast as I can. That's the realm of what we call optimal controls. A little case of what that stuff is at the end of this class. But mostly we're going to concentrate on the first one. So let's remind ourselves of characteristic equation, characteristic roots. So we're going to design for the root of the characteristic equation, basically all the poles in the system. I will specify the poles and then figure out what the controller has to be to get me those poles. Characteristic equation means homogeneous equation, which means internal dynamics, which means transient response. Right? Remember that. We're designing here, well, really what the transient response is for the system. How much overshoot do I have? What's the settling time? What's all these terms, things that we did in the transfer function controls we'll do here. Oh, let's remind ourselves of some of these transient response. For first order transfer function, solution to it is exponential. State transition matrix showing up there, right? Times initial condition, supposed to be initial condition, right? And I can specify things by, usually what we'll do is called time constant system, which is 1 over the signal. Right? And remember the response to this exponential, this transient response, starts at t equals 0, value 1, and then as t gets larger, it goes off to 0. Right? Exponential decay. At the time of 1 time constant, it will be at 37% of 0.37. Start from 1, at 1 time constant it will be 0.37, and t equals infinity goes to 0. Okay? Remember that one? Second order. Well, second order roots. There's a real part and imaginary part, right, which is sigma and omega d. Sigma is the damping ratio times natural frequency. Omega d, the imaginary part, is what we call the damping natural frequency, which is the natural frequency square root 1 minus a squared. Right? Hopefully you remember that relationship. And I can rewrite this thing and solve for it. And the time solution for a homogeneous solution, or impulse response rather here, is constant and exponential. And notice the exponential is decays according to the real part, and a sinusoidal part, that's the frequency of the imaginary part. Right? The response of this. We've seen this before. It depends on damping ratio, of course. So if I have a damping ratio of 1, so it's 0, goes up, exponentially decays to 0 again. The lower the damping, the more oscillatory it takes, and the longer these oscillations take to die out. Right? They die out at the rate of the exponential. Okay. So we'll go through some more examples of how to choose these poles and whatnot. So that's what we'll be designing with. So let's look at what we call state feedback. So once I've defined the pole locations, I've really defined my desired characteristic equation. So now I have to see how to implement that. And the idea we'll start off with is that I will be able to monitor and observe every single state. Right? I can put a transducer and measure every single state. The controller down here is in the feedback. Right? For transfer function systems, the controller was where? Up here in the error signal. Right? But now we're going to design here, because we're going to take look at every single state, do something with every single state, and drive the system. Right? That's the principle. Now, right off, we're going to let the input be 0. We'll see how to handle different types of inputs first, but for designing the system, let's look at input being 0 for the moment. And this controller is basically going to be a set of means, constant means. Future will vary. So what's U? Input to the system. Minus k times x. Right? So what's driving the system, right, is states times k. And I put a minus sign here. Not everyone puts a minus sign there. It doesn't really matter. Minus sign will show up as needed.